Okay, let's say you're given silver chloride added into a 0.01 molar HCl solution, aqueous solution. Compare solubility of silver chloride in pure water to its solubility in the HCl solution. Okay, in pure water, the silver chloride ionizes to silver and chloride, a 1-to-1. So at equilibrium, X and X, and KSP is equal to 1.8 times 10 to the minus 10. So solubility is the square root of KSP for a 1-to-1 ionization, square root of 1.8 times 10 to the minus 10, and moles per liter, and 1.34 times 10 to the minus 5 molar in pure water. Okay, in presence of 0.01 molar HCl aqueous, which will give you a 0.01 molar hydronium ion, which equals, and 0.01 molar chloride ions in the system. So the chloride would be the common ion, and you would see AgCl still ionizing to Ag ion, silver ion, and chloride ion, but this time you're starting with 0.01 molar in chloride. It's going to deliver X at equilibrium. So X now represents the solubility of the silver chloride. So the KSP expression is silver ions times the chloride ions, and this gives us 1.8 times 10 to the minus 10 to equal silver is X, and we have the 0.01 molar in chlorides. And so solving for X, we have 1.8 times 10 to the minus 10 divided by 10 to the minus 2 molar, which leaves us a solubility of 1.8 times 10 to the minus 8 molar. So there is a significant reduction between the pure water and the presence of the common ion when common ions are involved in the equilibrium. Okay, now I need to look at the solubility of a salt in the presence of a complexing agent. Now, what's a complexing agent? A complex agent binds chemically with the ions delivered into solution by the salt, and essentially forms a more soluble compound which removes that ion from the equilibrium and shifts the compound, salt, more into solution. Example would be silver chloride. Typically goes to silver and chloride ions. Its solubility is the square root of KSP in pure water, which is square root of 1.8 times 10 to the minus 10 molar, and silver and chloride ions, which is 1.34 times 10 to the minus 5 molar in pure water. Now, in complex solution, such as ammonia, if silver chloride is added into water, it gives silver and chloride ions. And if ammonia is added into this, ammonia will react with the silver very quickly to produce a silveramine complex like that. Of course, this is no longer an ion in solution, so essentially the net reaction, this cancels, that cancels, and we have silver chloride as a solid plus 2 NH3 goes to silveramine complex 2 plus chloride ion in solution. Now, as the silveramine complex is formed and the silver is essentially taken out of the equilibrium, and this will cause the reaction to shift to the right. So the complexing agent functions to increase solubility of salt by forming the complexing agent, complex structure, and removing one of the ions from the equilibrium, therefore making more salt shift to the right by Le Chatelier's principle and so forth. Say, for example, if we had at equilibrium a, I don't know, 0.10 molar in ammonia in the reaction, then we have equal amounts of the complex and chloride delivered. We could say a K complex expression would be the silver amine ion, chloride ions in solution, and that's divided by the ammonia concentration right there. And of course that is x squared over 0.10, and that's equal to the complex. However, this is a net reaction when you add the ionization reaction of the chloride to the complexing reaction here, and it is the product of the two individual K values. So this K complex would be KSP from the silver chloride times the K of formation of the silver amine complex. So KSP here times the KF is, we can look that up, or is given 1.8 times 10 to the minus 10, and this is 1.7 times 10 to the 7th for the fluoride formation of K. Well, that gives us 3.06 times 10 to the minus 3 right here. So we can take x squared over 0.10 to equal 3.06 times 10 to the minus 3, which gives x to equal square root of 0.10 times 3.06 times 10 to the minus 3 molar for the solubility, and that gives us a 0.018 molar solubility. And so you can see the pure water solubility is a 10 to the minus 5. Well, this one is a 10 to the minus 2, a significant increase. And of course the solubility and the complex agent was around 10 to the minus 8. Okay, so let's see. Was equal to 1.34 times 10 to the minus 5 molar, and common ion, it is 1.8 times 10 to the minus 8 molar, and in complex ion is 1.80 times 10 to the minus 2 molar. So you can see the increase here with the complexing agent, the significant decrease with the common ion, and this is your reference standards. That's what it would be in pure water.